In this video, we will discuss about medium transmission lines. So transmission lines come into medium category when the distance or the length of the line is between 80 to 200 kilometer and the voltage is between 20 kV to 100 kV. Now, when we have discussed short transmission lines, we have neglected the line capacitance. But as the length and voltage of the lines increase, the capacitance also will have greater importance because the effect of capacitance cannot be neglected. Now, the capacitance is uniformly distributed over the entire length of the line. However, in order to make the calculation simple, the line capacitance is assumed to be lumped or concentrated in the form of capacitors, which is shunted across the line at one or more points. Now, depending upon how we consider or how we place the capacitance or the capacitor, there are three commonly used methods for the solution of medium transmission lines, and they are end condenser method, nominal T method, and nominal Pi method. So we'll discuss one by one. First is end condenser method. There we'll place the capacitance at the end of the line before the load, connected in parallel with the load or in shunt. Therefore, here we have the sending end voltage, sending end current. Then we have the series connected resistance and inductance together constitutes Z. Then we have the capacitance. So actually, capacitance is 1 by Xc, and 1 by Xc is nothing but it is the capacitive reactance. So we normally take the reverse of the capacitance, that is reciprocal of the capacitive reactance. Therefore, we get it as admittance Y. So we know Xc is 1 by omega c or 1 by j omega c. Therefore, Y is 1 by 1 by j omega c. That will give you j omega c. That is why it is written like this. Then we have the load. Across the load, we have the receiving end voltage, and through the load, we have the receiving end current. So we have to analyze the circuit by simple circuit equations. So in the last video itself, I told you Vs and Is has to be expressed in terms of Vr and Ir. So that is our aim. So to start with, we'll express Vs in terms of Vr. So since Vr is the receiving end voltage, I can write Vs is equal to Vr plus Is into Z. That is being written here. That is equal to Vr plus, now Is is nothing but it is Ic plus Ir. So Is, it is being split to Ic and Ir at this point. So Is is equal to Ic plus Ir into Z. That will give you Vr plus. Now what about Ic? Ic is the current through this admittance. So we can write Ic in terms of voltage and admittance. So Ic is equal to Vr into Y. Actually, Ic or the current will be Vr by capacitive reactance. Now 1 by capacitive reactance will give you admittance. So that is why I have written instead of Ic it is equal to Vr into Y. So Ic plus Ir into Z becomes Vry plus Ir into Z. That is equal to Vr into 1 plus Yz plus Ir into Z. So we have got Vs in terms of Vr and Ir. Similarly, Is is Ir plus Ic, and Ir we can write it like that itself, and Ic is Vr into Y. So Is is also being expressed in terms of Vr and Ir. So in the matrix form we can write it like this: Vs Is is equal to, here this should be the coefficient of Vr in the expression for Vs, and that is 1 plus Yz. Then we have the coefficient of Ir, that is Z. Then the second equation, that is the equation for Is. Here we have to write the coefficient of Vr, that is Y, and here you have to write the coefficient of Ir, and that is 1. So we get the matrix, or we represented the medium transmission lines using end condenser method as a two-port network. Then we have nominal T representation. So nominal T representation is nothing but we have to express we have to consider the transmission line in the form of capital T, alphabet T. For that, what we have to do is we will lump the capacitor at the middle of the transmission line. At the middle of the transmission line means if the total impedance of the transmission line is Z, onto the left side of this capacitance we have impedance Z by 2, and onto the right also we have the impedance Z by 2. So we are lumping the capacitance at exactly the midpoint of the transmission line. And similarly we have to draw the circuit. So we have the sending end voltage, the sending end current, then we have the half of the resistance, that is R by 2, and half of the reactance X by 2. Then here we have IR, half of the resistance R by 2, half of the reactance X by 2. Then we have the load, and across the load we have IR. And this is the lumped capacitance or the admittance Y, that is equal to J omega C. Current through the admittance is IC, and the voltage across the admittance is VC. So we have to perform the same analysis here, that is we have to express the sending in current and sending in voltage in terms of receiving in voltage and receiving in current. So we'll do one by one. We know actually Vs is equal to this is Vs. Vs is equal to Vc plus Is into Z by 2. And what is Vc? So we have to replace Vc with Vr. So Vc is what? Vr plus IR into Z by 2. That is being written here. Vc is equal to Vr plus IR into Z by 2. Is is IR plus IC. Instead of IC, I can write Y into Vc. So that is equal to IR plus Y into, instead of Vc, we can write Vr plus IR into Z by 2. So Is is equal to, rearranging this, YVR plus IR into 1 plus YZ by 2. So we have expressed Is in terms of VR and IR. Next, our aim is to express Vs in terms of VR and IR. So I already told Vs is equal to Vc plus Is into Z by 2. So that is equal to VR plus Is. We know what is it. So substituting for Is, I can write it as IR into Z by 2 plus YVR plus IR plus IR Z Y Z by 2 IR into Z by 2. So we have to rearrange this such that we get a term with VR and a term with IR. So we'll be getting Vs is equal to VR into 1 plus YZ by 2 plus IR into Z into 1 plus YZ by 4. Then our next step is to represent in the form of a matrix like this. Now we have to draw its phasor diagram. Now to draw the phasor diagram, always take VR as the reference phasor, then go back to the circuit up to Vs. So here after VR we have to represent IR, which is lagging VR by an angle phi r. Now this IR, when it passes through R by 2, it produces a drop IR into R by 2 that is actually in phase with IR. But since it is a voltage component, it will be represented over this along with VR, not with IR. So this is IR into R by 2. Then we have a term IR into X by 2 that will be in perpendicular with IR into R by 2. So it has been drawn like this. After this, you have the current IC from the figure. This is being drawn with respect to the figure. After IR, you have to draw this current IC. Now IC, it is the current through a capacitor. Now we know the current through a capacitor will be leading its voltage by 90 degree. So what we have to do is the resultant vector of IR into R by 2 and IR into X by 2 will be VC. So the current IC should be in phase with VC, but since it is a current component, instead of drawing along with VC, it is drawn in such a way that how it is drawn to be here. That is, if we draw IC with respect to VC, it will be like this. So, the same way or parallel to this, I have drawn IC from IR since it is a current vector. So, this IC, now the resultant of IR and IC will be IS. Now, after getting IS passes through R by 2 and X by 2. So, we have two components, IS into R by 2, the voltage component, and IS into X by 2, that is also voltage component. So, IS into R by 2 will be in phase with IS, but instead of drawing it over here, what I have done is I have just transferred it to this point. So, I will get IS into R by 2. Then perpendicular to IS into R by 2, I can draw IS into X by 2. And this resultant will be IS into Z by 2. If we join this point E to the origin, we get Vs. Now, after getting Vs, I can draw the angle between Vs and Is as phi s. It is phi s is the angle between Vs and Is. Now, the next one is the nominal T Pi representation. So, in this representation, we have to represent the line in terms of pi. So, pi, we know we have two shunt elements. So, what is being done is y, the admittance is divided into y by 2. So, we'll have a series resistance, inductance, and two admittances. Similarly, we have Vs, Is, then IL, IR, VR. Then the current through this capacitance or admittance is IC1, and here it is IC2. So, we can discuss this. So, Is is equal to IR plus IC1 plus IC2. That is equal to IR plus IC1 is VRY by 2 and IC2 is VSY by 2. So, Vs is equal to VR plus IL into Z. Substitute for IL as IR plus VRY by Z. So, we will get Vs in terms of VR and IR like this. Then we can go and substitute for this in equation 1. That on rearranging and solving, I will get Is in terms of VR and IR. Then I can represent it as a matrix like this. After that, I can draw the phasor diagram. Here also, I'll draw the phasor diagram by taking VR as the reference vector. After VR, I have a current IR which will be lagging VR by an angle phi r. Now, IR, coming back to this circuit. So, I have drawn IR. Next, I have to draw IC1. IC1 is the current through Y by 2. Now, the voltage at this Y by 2 is VR itself. So, actually, IC1 should lead VR by an angle 90. So, I should actually draw IC1 over here, but instead of drawing it over here, I have drawn it here since it is a current component. So, this is IC1. Resultant will be IL. Now, when IL passes through R, it produces voltage drop IL into R, that is being drawn here. Now, it's perpendicular to this ILR, I have IL into X. When I join this, I get Vs. After getting Vs, after getting Vs, I have to draw IC1. Now, IC2 actually. IC2 will be leading Vs by an angle 90. So, instead of drawing it over here, I have drawn it here. So, this should be IC1. So, instead of drawing here, I have drawn it here, that is IC2. Then resultant will give you IS. So, the angle between Vs and Is is phi s. So, that's all about medium transmission lines. Thank you.